Alrighty, Algebra 2 nerds. I just realized this is the first time you've seen one of these things, huh? So when I record my notes, I have these little artworks that students have made for me. This was Daniel Quevedo. Is that how you say his last name? Quevedo? He's in band. I don't know. He drew this up for me last year. If ever you want me to have new artwork, you let me know. I can give you one of these Mr. McCutcheon papers, and you could do whatever artwork you want on it as long as it's appropriate. Anywho's we are going to continue lesson 1.3. I'm hoping to finish it today. Fingers crossed that it gets finished today. What we learned 2 days ago was positive, negative, increasing, decreasing. And I drew this little cute roller coaster guy, and I told you, remember that your graph can be thought of as a roller coaster track. If your roller coaster is going down as you go left to right, decreasing, and if your roller coaster is going up as you go left to right, increasing. Please, for increasing, decreasing, positive, negative intervals, only use x values. So we say, where is something happened? That's the x's where it's occurring. Where is my graph decreasing? It was decreasing from negative infinity because there was an arrow all the way up to that x value, which we estimated. And then it was decreasing again from this x value to this x value. And then it was decreasing again from this x value to this x value. So on and so forth. Positive or negative again was where you have y values that are positive, where you have y values that are negative. So we're using the x-axis numbers to describe where we're positive, where we're negative. All right, so what were the barriers for positive and negative? That one's easy. The x-axis. Those are the barriers, and that's why I put those green dots there and did that in green. But where are the barriers for increasing, decreasing? I mean, I put the blue dots. That would have been a barrier. But what do we call those things? We call these x-intercepts. What do we call these things, though, is the question. And that's where the lesson begins. We call those extrema. Extrema. There's a lot of words here. I'm gonna give you the TLDR, okay? The too long didn't read. Extreme values are going to be highest points and lowest points. Not the incredibly highest, not the incredibly lowest, but they're going to be dips and like hills and valleys, essentially. Here's a lowest point, here's a highest point, here's a lowest point, here's a highest point. It doesn't mean it's the biggest overall or the smallest overall. It just means in its local neighborhood, that's a low point. In its local neighborhood, that would have been a high point if it was a closed dot. In its local neighborhood, that's a closed dot, or that's a minimum. Oh, I just realized also, if you're watching this video directly after the 1.3a video, I altered this picture to give better notes. In my old version, I let those two stay closed. But a couple days ago, I made the executive decision that it was a better example if I opened those, which is why these answers changed a little bit. But that only matters if you actually watch the 1.3a video. I changed this example. Anyway, so low point, high point, high point. Cool? You can think about it like if it rained on the graph. Water would collect here and water would collect here. Those are low points. Water would wash away from here and water would wash away from here. Those are high points. Okay? End points count as extreme values. So this would be considered a minimum. End points count. Open dots don't because that point doesn't exist. But end points count. Arrows don't because that's not a point. Cool? Make sense? The only other thing that we'd have to discuss then is, what about the words local and absolute? Local means in that small neighborhood. Absolute means of the entire graph. So this graph has a local minimum here and a local minimum here, but because it points down forever, it does not have an absolute minimum, also known as a global minimum. This graph does have an absolute maximum, global maximum. It has two maximums. This one happens to be global/absolute. This graph points up forever. So even though it has a local maximum here, it does not have a global or absolute maximum. This graph has two minimums because I opened that dot, so that one doesn't count. This one is the lowest point of the graph, so you could say that this local minimum is also an absolute or global minimum. Okay? I'll never be picky with you and you go, oh, local minimum, and I go, wrong, absolute minimum. I'll never do that. Yes, that is a local minimum. And yes, that is a local minimum. If I ask you, is there a global or absolute minimum? The answer to that question here is yes, and it's right there. Okay? That's what all that crap says. Use the graph to find the extrema and the x values where they occur. Essentially, what I want you to do is say where the minimums are and where the maximums are. And we're just going to do them as x, y's. Maximum values, those are tops of hills. We'll have to estimate that one. This graph has two maximums. They are both local. Because this graph has arrows that point up forever, there is not a global / absolute maximum. Doesn't matter. But it does have two local maximums. Oh, I switched the color on myself. Pooh. Okay, well, I don't want to have to, I'll just switch the colors I wrote those words in. Sorry. I like to color code my notes. But before I go on, a hand went up. Yes, ma'am. So I won't ever make you classify. I basically just say where are the minimums, where are the maximums. I'm pretty sure that on a test I've never said what is the absolute max or min. I don't, because to be honest with you, other than saying, oh, that's the biggest one or that's the smallest one, nobody really cares. Okay. The only time those kinds of things ever really matter is in what we call as optimization or minimization problems, where you go like, hey, you're trying to build a box and you're trying to maximize the volume of the box while minimizing the cost to make the box. That's really the only time that you would care if it was a highest or a lowest. And like the ultimate highest or the ultimate lowest, okay? So don't worry about that. So where are my maximums? I have one at negative, that looks like -3 to me. Because see the x-axis and y-axis both counting by 2's. That looks like it's going to happen at the coordinate -3, 2. Let's be really specific here though. This is where it happens. This is what it is. Anytime you say where is something happening, you're talking about an x. This graph has a maximum value at x equals -3. That maximum value is 2. So where is x? What is y? Cool? It's okay with that idea? And we have another maximum going on at 2, 6. So I could say, where does the graph have maximum values? And you would say at -3 and 2. Not what are the maximum values. Okay? We really focus a lot on the x-axis. It really does get priority. This graph happens to have 3 minimums. And we're going to have to estimate them. Whatever, we'll do our best. This one appears as though it's at -6, -7. This one looks like 0, -4. And we'll say this one is 5, -5. I know it's offset a little bit, but whatever. So these are not intervals. These are coordinates. And we recognize them as coordinates because how could you have a maximum or minimum interval? That doesn't make any sense. Okay? It must have been a coordinate. These maximums or minimums will always be where your graph changes between increasing and decreasing. So anytime a graph changes between increasing and decreasing, it will always happen at an extreme value. Always. Every single time. Either at a maximum or at a minimum. And remember, those x values get brackets when we describe our increasing, decreasing. Just reviewing that. Comfortable? So graphs change positive, negative only at x-intercepts. Graphs change increasing, decreasing only at local extrema. Mins or maxes. Cool? Not always, but that's the only place it can happen. All right. So this one says use graphing technology to find all the extrema and the x values where they occur for the function. I'm not teaching you how to use a graphing calculator in this course. We'll save that for AP Pre-Calc. So then what are you supposed to do? Just go to Desmos and type it in. Okay? For your homework, and I don't think I gave you anything like that in the homework. So just pretend we're going to Desmos. And the only reason why I'm not actually going to Desmos is because if I pull Desmos up, it won't show up on the camera. So it'll just be my voice staring at this white space while you guys in the room see Desmos. Because it's this camera that's actually recording. It's not what's on the screen. It's the camera that's doing the recording. And Desmos wouldn't be under the camera. Anyway, this is what we would see if we went to Desmos. So we're just going to draw a sketch. And we're going to put no numbers on the y-axis and only 5 numbers on the x-axis. I'll do my graph in orange. This graph has 4 x-intercepts and does this. It looks something like that. And since I'm not going to ask you to do this on the homework and I can't ask you to do it on the test, I'm just going to show you where one of the values is. There happens to be a minimum here-ish. I've done a poor, picture not drawn to scale. I've done a really poor job of drawing my scale. I'm sorry. And I'm going to tell you the coordinates there. This is a minimum. Negative 2.057, comma, negative 24.057. It has another minimum here between 1 and 2, and it has a maximum between 0 and 1. But I'm not testing you on this, and I just want you to know where you would find it. Yes, ma'am. Oh, I pretend you graphed it on Desmos. If you go to Desmos and you type this in, it looks like this, and it hits the x-axis in those places. And then if you click on the graph on Desmos, it'll actually show you a coordinate here, and you can just hover over it, and it'll give you the xy. But you don't have to know how to do that. We'll learn how to graph this later in the year. For now, I just need to know, can you identify what maximum and minimums look like, and can you do positive, negative, increasing, decreasing? Awesome. Now we get to learn, oh, before I do that, questions on increasing, decreasing, positive, negative, extrema, x-intercepts, any of that stuff? None? Okay. His pencil's moving. Can I turn the paper over? Brady? Yes. Okay. Don't panic. I can always come back to it. Okay? Boom. Here we have a table that has 4 types of in behavior. These are not the only types of in behavior, but here are 4 really common ones. Up and to the left, up and to the right, down and to the left, down and to the right. When I ask you to describe in behavior, I'm asking you to describe it using symbols, not words like I just did. Okay? Mathematics is a symbolic language. Like a lot of our Southeast Asian languages, where they don't have an alphabet, they just have symbols that represent words. Math is like that. Just to prove a point, this is a statement that I wrote in mathematics. It says there exists an x such that x is an element of the real numbers and x is calculated by finding 2n plus 1. However, n has to be a natural number. See, I just said a lot of words. That's what that says to mathematicians. There's symbols in mathematics. Okay? My point is, we try not to use words in mathematics, we try to use symbols because it's more compact. I don't like words, I like math. So what are the symbols for up and to the left? And actually remember, x comes before y, so I should say left and up. It works like this. I have to write one word. and that word is as. As x goes to, what kind of thing can we find out to the really far left on the number line? Negative infinity. What do we find up really high on the y-axis? Positive infinity. There you go. That is how you describe left and up. As x heads towards negative infinity, y heads towards positive infinity. See, symbols are faster than words. Left, up. If you need to make yourself a note, this is left, this is up. Wrote in blue, so I'm going to write in orange. Go Gators. This one is right and up. If really far left in the number line got me to negative infinity, I don't think it's much of a stretch of the brain to say really far right is positive infinity. And we already know what up is. Those are arrows. They're just really short. Ta-da! No, it's an X, not a K. X's and Y's. I didn't pick the pin up high enough and the roller ball dragged a little bit. Now we're going to say left and down. As x goes to negative infinity, because that was left we said, y, guess what's down? One of the ladies whispered negative infinity. Yep. This one is right and down. That purple pin has not been used yet, apparently. We already know that right is x going to positive infinity. We already know that down is y going to negative infinity. So these are the 4 in-behavior options for polynomials. You don't have to know that yet. I'm just letting you know. That'll be later on. You don't have to know that yet. It's later on. This is a polynomial. So when we get to graphing these things, I like to call them spaghetti graphs. So they always look like noodles. They only have 4 options for endings. These are those 4 options. For now, I just need you to know how to describe your options. Okay? Questions on how to describe these using those symbols? None? Okay. Then, let's use those symbols to describe the end behaviors of these 2 pictures. Trying to decide what colors I want to write in. You know what? Halloween is coming up soon. We'll go with orange and purple. Okay. We read our graphs from left to right, so we might as well describe the left side first. We said going to the left is x going to negative infinity. And as x goes towards negative infinity, so as I head to the far left, we'll check out this graph. Both arrows point up. So on both ends, what is y heading towards? You guys can just shout it out. Positive infinity, or you could just say infinity. And that's happening to the left and to the right. Ta-dur. For now, yes. I say it like that because in AP Pre-Calc we'll introduce more symbols so that you don't even have to use the word as. And instead of putting this comma and mentioning x and y, there's a way of writing it as one thing. But in Algebra 2, this is how we want you doing it. And this is how it'll be assessed. Now we're going to do it for this one. Starting on the left. as x heads towards the left side, which is negative infinity, lots of voices. What is y approaching? Negative infinity, because this bad boy points down. And on the right side, just like this one, I'm shaking, I'm hungry. As x goes to the right, which is positive infinity, y is going up to positive infinity. Now, we're not done with the notes, so don't go packing up. We are going to add stuff to the back of this page. And by we, I mean you, because mine already has it, I think. It should. Yeah, mine already has stuff on the back. Now, before I flip the paper over, this is a review question about symmetry, because I see a lot of my students are struggling with symmetry already. And you're not alone. Ms. Bluebaum's students are struggling with symmetry as well, because she was in here discussing it with me. I'm looking for all, I think there's 30 of you, to answer me. The answer is yes or no, okay? I want to hear all voices. Even, okay, you guys are hearing me? Class, does this graph have odd symmetry? Lots of people said no. Lots of people, what does that mean is an important question to ask. Here's even and odd symmetries. It's okay. I'm saying it's an important question. But you copied the notes, right? Sounds like, I think what you meant to say was not yet. Because you're going to this weekend, because it's an important concept. Yes. Graphs that are evenly symmetric have the y-axis as an axis of symmetry. The y-axis cuts them in half perfectly, like it's a pair of hands that can close. Graphs that are oddly symmetric must be centered at the origin, and turning them upside down across the x-axis is the same as turning them left-right across the y-axis. So, does this graph have odd symmetry? No, it does not, because it is not symmetric around the origin. It does have point symmetry, but I'm not going to assess you on that. This is neither even nor odd, exactly. Okay, now, even will always have the y-axis acting as a mirror. Yes, we're not finished either. So, if you would please flip your paper over, I'm going to pause the video while everybody in the room adds this table to the back of their paper. Let me zoom out a little bit. Once it's in focus, I will pause the video, and everybody in the room is going to draw this table. Don't worry, it's coming. Okay, so first, just so you know, if well, it wouldn't be for any of you guys that are currently in the room, but from now on, this will show up printed for everybody like it is in mine. Now, what happened for you guys in this room right now this year is I realized after I ordered the notes that I needed to add something to the notes. So unfortunately, that happened this time, but I'm hoping for that to never happen again for you, okay? So you should already have everything in your notes for the future. Anyway, this word is pronounced asymptotic. It describes what's happening around an asymptote. Asymptote. So first of all, what is an asymptote? An asymptote is a line that your graph will approach, and it will get infinitely close to it. So that is the definition of an asymptote. What you have on this page are vertical asymptotes and horizontal asymptotes. Because vertical's up, down, horizontal's left, right. Are there others? Yes, and we'll see them later in the year. For now, I just need you to be able to describe what's happening around vertical asymptotes and horizontal asymptotes. Call it asymptotic behavior. There. Got that out of the way. I want to do the horizontal ones first. Notice And you don't have a picture down here. Don't worry, we'll draw it in a second. For the future, they already have it printed. It'll be in the notes from now on. But for you guys, we'll draw it, okay, in a moment. The first question that I heard, and was while the video was paused, is what does C mean? So we're using C to represent the word constant. Means a number. So every one of these is y equals some number. Any number. Y equals a number. It could even be y equals 0. It's just some number. And we use C in mathematics because the word constant starts with a C. Okay? Y equals a number is always a horizontal line. So the equations of these horizontal asymptotes would be y equals and then some number. Okay? So what we have here are these graphs approaching some y value. Something on my paper. Oh, that's where I scribbled on the other side. So let's describe this behavior. Notice that in these two on the left, my graph is heading to the left. Yes? So both of them get as x is heading towards negative infinity because we're heading to the left. And they have the same y behavior. For both pictures, your y value is heading towards C, because C is a y value. This one is, as you're going to the left, your graph is going to get closer and closer and closer to this y value. It'll always be slightly above it, but it will forever get closer and closer and closer. This one, as you head to the left, your graph is getting closer and closer and closer to this y value. It'll always be below it, but it's going to get closer and closer and closer to it forever. Okay? Then how are these different? Literally just because they're pointing to the right. That's the only thing that makes them any different. So instead of x going to negative infinity, x goes to positive infinity. So as you head to the right, your y values, either above or below, it doesn't matter, will be approaching that number. Whatever that number is. So for example, if your graph is approaching the x-axis forever, that would be y equals 0. Your y values will be heading towards 0. So these are still technically end behaviors because we allowed x to go to one of the infinities. So those are still end behaviors. It's just an asymptotic end behavior. Would you like to ask me any questions about the symbols or why they are what they are? No. Okay. Just so we're clear on this. If you're describing this from left to right, this is increasing. If you're describing this from left to right, this is decreasing. If you're describing that from left to right, this is decreasing. Will it go down to negative infinity? No. But it will decrease for all eternity as it goes to the right. It just does it really, really slowly. And as you go from left to right, this is increasing for all eternity. Will it ever go above this line the way the behavior shows? No. But it'll just get closer and closer and closer for all eternity. So that it's still technically increasing. Okay? Yes, Ms. Ram. Okay, great. I'm glad that you said that. For my future students, you have this image. For my current students, you do not. So we're going to draw it. Notice that this graph does not have any dotted lines on it. That is because the dotted lines are not actually part of the graph. We put them on there for us so that we can see where they are approaching. So I'm going to put a red dotted line at the line x equals negative 3. Oh, wait a second. I didn't finish the table, did I? Well, I'm going to finish this image, and then we'll go back and finish the table. I'm not really sure what just happened to my brain. Sorry. I didn't finish the table. Bad math teacher. Bad. Don't worry. I'll bring this image back. I'll bring it back. Let's get on this table. These I saved for after these because they are different. And here's why. Like you can see in this picture, if I were to put that red dotted line right there, boop, 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 boop. Notice that on the left side of it, my graph is acting differently than on the right side of it. That is really common, that your graph will act differently on the two sides of a vertical asymptote. What that means is when we describe how x is behaving, we need to actually say which side we're on. Can we agree that we're on the left side of x equals whatever that c value is? Here's how that looks. We use that little superscript where an exponent would normally be, and you put a minus sign. That means on the left side of c. That means numbers slightly less than c. So for this one, we would say, as x heads towards c, but is always slightly less than c, so on the left of c, y values are going up. So when you're describing asymptotic behavior at a vertical asymptote, it's important that you say which side of the vertical asymptote you are on. It is important. For this one, you're on the right side of the vertical asymptote. So it gets a little plus sign. That means a little bit bigger than that x value. So if that was at like x equals 5, this might, you could have an x value of 5.00000001 because that's a little bit bigger than 5, isn't it? So we'd say as x heads towards c, but you're always just a little bit to the right of it, y goes to positive infinity. And then these are the exact same trick, only for these, y was heading to negative infinity. So the little minus sign as a superscript means to the left of, and the little plus sign as a superscript means to the right of. I'm out of space, so I'll just go down. Oh, I forgot to change the color. Man, that's boring. And because I had to wait for you to draw this, I ran out of time to do the last example. I'm going to do it in the video, though, just because I don't want to have to re-record this video. So I'll pause it and do it between classes. All right, so I'm just going to go ahead and finish these notes because in the future I will be able to finish them in class. For this last example, like I said, we're going to have this vertical asymptote. The dotted line is not part of the graph, but it's drawn on there to help us really see what's going on. And I already said it, but this was at x equals -3, and this is at y equals -2. And we are just going to describe our asymptotic behavior. Let's do the left-right first. Let's handle the in behavior. Out here, as x is heading towards the left, which was negative infinity, I hope you can see that this thing is getting really close to y equals -3. On the right side, you're also getting close to -3. So we write it like that. Now the asymptotic behavior that's happening at this vertical asymptote, remember we have different behavior on the left side than we do on the right. And that's why we have to use those little superscripts. Left side first, since we go left to right. As x approaches the number, I just realized that I wrote those values wrong. Anyway, sorry about that. That's a y, that's an x. I'll be okay. As x approaches -2 from the left, so I'm over here, just a little bit left of -2. My y values are shooting down. Oh goodness, I put equals. See, I'm in a rush. You see what happens when you're in a rush? Make stupid mistakes. These are not supposed to be equal signs. They're supposed to be arrows. Because they're not equals, they're heading towards. And lastly, as x heads towards -2, but I'm on the right side of it, so just slightly bigger, y is shooting straight up. And like I said, future classes will have finished that in class. Anyway, thank you, nerds. Appreciate you.